All right, so this video is going to be on organometallic reagents with other compounds. So, for example, phenylmagnesium chloride with CO2 and acid. It's going to get you a fun little carboxylic acid. And once we're done with these types of reactions, we're going to talk about the alpha beta unsaturated carbonyl compounds, as well as some synthesis type problems. Okay, so this reaction in particular, I did in lab a lot when I was doing research, and it's just nice to, you can use carboxylic acids and further synthesize them to a variety of things, and so it was pretty useful. Your source of CO2 might actually be like, sorry, you guys know how to do this reaction, so that's why I'm not really going over it, but here, let's detect that electrophilic carbon in between those two oxygens. And then that's where we get our carboxylate, which of course the acid protonates to get our carboxylic acid. Okay. But what I was going to say is the CO2 is usually going to be like dry ice, for example. So I did this reaction at minus 78 degrees. And then throw in a little dry ice, and voila, you get your carboxylate, and then you acidify that, and boom, super fun. All right, so we got our carboxylic acid. In this case, this is cyclohexane, not the benzene, right? But the same thing, it works pretty much whatever, any kind of Grignard or organolithium reagent that you can make, you're good to go. So let's take a look at this guy, methyl ethyl propyl. So chloropropane, hit that with magnesium. You get your propyl magnesium chloride, right? CO2, a little bit of acid, and then we've got our carboxylic acid. So for me personally, I need to count my carbons 1, 2, 3, 4, especially when we have Grignards and organolithium reagents. I've said this before, I'll say it again. Label your carbons so that way you don't lose track. Label that other one, the CO2 one, as a little blue, and that way you can kind of, all the carbons are accounted for. And you don't have too many, you don't have too little. And then easy peasy from there, right? This reaction is pretty straightforward. Let's say we got this guy, same deal. Hit it with a little magnesium, make a Grignard, hit it with CO2 and acid, get your carboxylic acid. So again, making sure you don't end up with the you got to have that extra carbon in between, really. So do your inventory. Okay. All right. So the next type of reaction that we want to go over with epoxide, or with Grignards and organolithium reagents, or reactions with epoxides. So we already know that epoxides are strained ring systems that will open up within the presence of a strong or a weak nucleophile, right? And so if we've got a organometallic reagent, then we can open up that ring. R minus is is what we're getting from those lithium or Grignard or cuprates, and so that's our good nucleophile. That's an attack and open up that ring. Okay. Of course, the water protonates it to make that alcohol. What we really want to remember from what seems like eons ago, forever ago, is that strong nucleophiles are going to attack at the least substituted carbon. Okay, so if you have an unsymmetrical epoxide, then you want to make sure that you're getting your stereochemistry, your regioselectivity correct. Okay, so for example, this guy, if we hit that with let's say phenyl magnesium bromide, we want to attack on the left side of that molecule, bust that guy open, we get our tertiary alcohol in this case. Okay, and protonate with water, sorry, I guess technically a tertiary alkoxide, and then we get our protonation with water, we get our alcohol. So again, you guys are stoked because this is easy stuff for you. It's just a lot of it's just going to be reminders, which is perfect because our synthesis game is about to be off the hook. But you got to get that practice in. Okay, so how would we form the following compounds from like ethyl magnesium bromide, right? So really, what you want to look at is if you have obviously like an epoxide with ethyl magnesium bromide, you want to look for that source of two carbon, or like where that two carbons would have been placed. And so it's not very difficult to kind of see it in this particular compound. Maybe the difficult thing would be getting your stereochemistry right. Technically, I don't need to redraw this, but I will. I'll put the dashes there for you just to get that stereochemistry lined up, because that molecule could have just been flipped over and it would have been the same thing. But for the sake of making it look pretty and make sense the way it is drawn, you would have it like this: attack from the top, and then remember it's like inversion of stereochemistry, right? So that ethyl group is on the wedge. So how would we make this guy? From the same reagents, like an epoxide and the ethyl magnesium bromide. So for me, I like to just think of that oxygen almost like attacking the adjacent carbon, because it's the reverse of an epoxide breaking open, right? So, and then you can how convenient. We've got our two carbons there where that carbon-carbon bond is forming, and so if we had that epoxide in our ethyl magnesium bromide, that would give us our desired product. Okay, so for me, I look at where the alcohol is, try and create a bond, a three-membered ring with the adjacent carbon. Then that tells you where your epoxide could be. Maybe there's only one spot like this guy. Maybe there's multiple spots, but in this case, it's super chill, super easy. Boom, we got our breakdown pretty easy. But if there's multiple spots, just keep trying, right? So in this case, we've got where the oxygen can attack on or kind of not attack. I'm saying, like, I'm just showing you like where the bond placement could be, right, on the top or the bottom. If we do the bottom, that's really going to get us where we want to go, because we have these two carbons here, which would be the source, which would come from that Grignard reagent, okay? And it busts that ring open, okay? If we did the epoxide on the other part at the top, we wouldn't be able to add just two carbons. We would have had to add at least three, so it gets a little bit trickier there. So yeah, I mean, that's how I break it down. Just basically form the epoxide first and then go from there. Alpha beta unsaturated carbonyl compounds. So this is pretty cool too. This reaction, well, it's fun, but it's also like not that difficult in terms of like conceptually, I guess. So alpha beta unsaturated is, so they have that alpha carbon, which is the carbon next to the carbonyl. Okay, so and then the next one would be beta, right? Alpha, beta, gamma, delta, or so on and so forth. So it does have a resonance structure because it is conjugated, right? So since it does have a resonance structure, if we draw the structure on the right, we have a straight up positive charge on that terminal carbon. And then on the left, we have a delta positive on the carbonyl carbon. Okay, so this is important because the nucleophile could technically attack either of those electrophilic sites. And really what we're going to do is show you what the resulting product from attacking those two sites, and then we're going to show you which reagents will selectively do that type of reaction. Okay, so let's say we have a nucleophile and water in our second step. What we're going to get in one of those reactions would be this allylic alcohol right here, right? And this is called a 1,2 addition. Okay, so a 1,2 addition product occurs because as you can see, the nucleophile adds to the 2 position, and then the hydrogen adds to the 1 position. Okay, the oxygen, 1,2 addition, straightforward, right? Now let's take a look at a different type of reaction, which I already showed you, but the nucleophile attacks that terminal electrophilic carbon. Again, it's got a straight up positive charge if you draw that resonance structure. What do you think this is called? A 3,4? No. That would be too easy. But I just want to label explicitly that blue hydrogen from the water because that's telling us where it came from, where it went, right? So it is technically on the 3 and the 4 position, but it's called a 1,4 addition product. What are you talking about, Willis? What are you talking about, Jess? Well, let me just do these mechanisms real quick for you, and then it'll clear it all up, and it'll actually make a lot of sense. And you guys are going to be like, dang, I know my stuff. So, 1-2 addition mechanism, I think this one's actually pretty straightforward, and you guys could probably already handle this one. You attack the carbonyl carbon, and then you get your alkoxide, and then you protonate that with water, right? And then that gives you your, remember, allylic alcohol, right? These guys are, it's fun to know the different types of products that you're forming and essentially what you can do with them. Who knows? So, the 1-2 addition product right there, okay? That one makes sense, the numbering. We don't want to throw anything at the wall or smash your computer, iPhone pad, all of that, whatever. The 1-4 addition mechanism isn't bad either. It's just the name is kind of silly at a glance. It makes sense if you do the mechanism though. Okay, so it also makes you feel smart because you're like, dang, I know what this means. It's almost like we're speaking our own language. Well, we definitely are, actually. This stuff is hieroglyphics as far as a lot of people are concerned. So let's get it. When we attack that terminal carbon, we can push the pi bond to get that the alkoxide, right? The O minus. And then what happens is you protonate it, okay? And if you protonate that oxygen, you get this vinylic alcohol. And if we take a little look-see, this actually makes more sense why it's the 1,4 addition product, right? The nucleophile added to the 4 position and the hydrogens on the 1 position. So the 1,4 addition, now it makes sense. But that's not the product that I originally drew, is it? That's because it is an enol, right? Remember Enol, remember the Enol Tautomerization? So the enol can undergo tautomerization, which is basically an equilibrium and it's shuffling the proton around. So we can move that proton off that oxygen and place it at the 3 position. And that's why our product doesn't look like it's a 1,4 addition, but it looks like it's a 3,4 addition. But so the 1,4 addition name you need to know because it does form the the enol, and then it undergoes tautomerization to form that final product, the ketone product in this case, okay? All right, so I told you I was going to show you the mechanisms, and then I was going to tell you what selectively does the 1-2 versus the 1-4 addition, okay? I feel like you could probably guess the one that's weird is probably not the, I don't know, the one that's straightforward I always find to be the Grignards and the organolithiums, right? Those guys are crazy. Remember, they are super reactive, right? So keep this in mind. The delta positive on the carbonyl, that's like kind of positive, right? So it's just like moderately electrophilic, at least relative to the resonance structure that we drew where we have a straight up positive charge on the terminal position, okay? So the way I think of it is the strong negative reacts with the minor positive because it can, right? Whereas the weak organocuprate is going to react with the straight up positive charge because he's weak sauce, right? Remember, the organocuprate's weak, and so it needs a little bit more help. It's less negative, so it's going to need a little bit more encouragement to attack, and that's going to happen when you have a straight up positive charge on that terminal position when you draw it. Obviously, that resonance structure in the matter. So a 1-4 addition occurs with the organocuprates, and then the 1-2 addition occurs with the lithium and the Grignard reagents. Okay, that's my justification for you. There's definitely, that's a super simplistic explanation, right? That has to do with HOMO and LUMO orbitals and things like that, which is kind of, we could talk for hours on that. So that's the explanation you're getting, and I hope it satisfies. So here we go. Some examples. What are we forming if we got that phenolithium? What are we forming when we have this organocuprate right here? So we got this fancy looking structure, right? It looks weird. Super common one that you'll see though. So if we have the organolithium, remember, we will attack that delta positive, right? The carbonyl, because it's kind of positive. We need something strong to attack there. And we got that with the organolithium. When we got the organocuprate, we want to attack that 4 position, that beta position. Okay, and when we have the alkene in parentheses, it's cutting off that bond to the carbon or the copper, and so that is where you want to break. It's 2 carbons. It's representing 2 carbons, and you need to make sure that you're only adding 2 carbons to your product. Okay, so that's the reason why I gave you this one, because it looks weird, and you're like, how many carbons do I have? I don't know. At least when I first saw it, I was like, I don't know if that's 2 or 3 for some reason. Even though now to me it seems clear that it's 2, but who knows, right? Like I said, hieroglyphics. So we got this guy right here. We're gonna do a couple more. So this, we want to make this using alcohols having less than or equal to 5 carbons. Okay, so anywhere in between 5 or less. We also want to make a bunch of these cyclohexane derivatives using cyclohexanol and ethanol. Okay, so other than that, I like these types of questions because they give you, it's free range. Like you can do whatever you want. So when you're doing these problems in your book and they give you the freedom to choose whatever reagents, that's making it difficult to look at the solutions manual, right? So as long as your reaction follows the rules, right? Like how do we make a ketone? How do we make an alcohol, right? Your synthesis problem or the way you wrote it up might actually be correct. It's just not what they wrote, because there's a million different ways you can create the same product. Okay, so the first problem, what my thought is 5 carbons, right? I don't know how to make a ring yet. We didn't really, I mean, we did kind of do that, but we're not super good at it. So let's not make the ring. Let's start with the ring. And it said we can start with 5 carbons or less. So let's start with that. Add just the 3 carbons, and really the only way we know how to make carbon-carbon bonds is like substitution reactions, but also chapter 17 we just learned how to do Grignard reagents and organolithium and cuprate, so why not do that with a carbonyl? So the question would be, which route do I want to take? Doesn't matter really on paper, so we're doing the reaction on the right. Okay, just because I think your book might give you the reaction on the left, so I'll do it differently. And yeah, I mean, it really doesn't matter in this case. So how will we make this cyclopentane magnesium bromide? We can work our way back. Remember, that's a retrosynthetic arrow to the bromide, and then work our way back to the alcohol. We're allowed to start with that alcohol. We know that if we hit that with PBr3, we're going to get our bromide, and then hit that with magnesium, we're going to get our Grignard. Okay, so boom. Moving on to the next one, we wanted to make that acetone molecule, right? So how do we do that? Well, we want to work our way back to an alcohol, right? So we're allowed to just start with alcohols of 5 or less carbons. So let's start with that isopropanol, hit it with PCC, we got our ketone, boom. Bada bing, bada boom, moving on, let's go. Take this set of molecules. We want to make all of these from, like I said, cyclohexanol and ethanol, okay? So again, your methods might be a little different than mine. Go ahead, pause the video, try them on your own, see what you get. I'm just going to cruise through it real quick though. And I also haven't really I didn't look at these, I just threw them on there. I'm going to try them. So we're going on the fly, that way you can hear me think out loud. So, got my cyclohexanol. Again, making carbon-carbon bonds. I mean, to me, that looks like a Grignard reaction, right? Or an organolithium, like a carbonyl. Hit that with the 2 carbon organometallic, and then you get your alcohol. So I want to hit that alcohol with PCC to get the ketone. Maybe hit the ethanol with dianyl chloride. I'm throwing a different reagent at you for just for review purposes. You get your alkyl halide. Hit that with elemental lithium. Gives you your organolithium. And then we attack, right? With a little bit of water, of course. Get your alcohol in the end. Moving on to B, it looks very similar to the to A, right? So if we're going to make A, why don't we just make A again? Same synthesis, right? Start with that alcohol and then hit it with PBr3, give us our alkyl bromide. Boom. Problem solved. Moving on, part C. This one's a little bit more tricky. We've got a ketone, right? And so we're going to get a little bit more crafty. Doesn't look anything like the first one, kind of, except we want to functionalize that part of that ethyl group coming off of the cyclohexane ring, right? So my thought is, how do we create a ketone at that position? I'm thinking an alcohol that's been oxidized. How do we get an alcohol there? Well, we want to do the elimination reaction from that alcohol product A. Gets our alkene here. If we do the hydroboration oxidation, we can get the anti-Markovnikov alcohol, right? So that's what we're going to do. And then we get our alcohol here at the least substituted position. Hit that with PCC, and we get our desired ketone product. Ooh, smooth. And then we get that terminal alcohol. Okay, so let's think about this one. If we want the alcohol at the end position, so when I look at that guy, like I said before, I want to put that oxygen on that adjacent carbon. Okay, if I did that, what would I have? I would have an epoxide, right? Now, how do I get an epoxide? How do I form that? I mean, I could form it from an alkene, like the cyclohexane with an alkene. I guess technically we can do an organolithium reagent, but for me personally, like, why not just make the epoxide and react it with cyclohexane magnesium bromide? So yeah, there's definitely options here. So you might go a different route. For me, I'm just gonna do cyclohexanol PBr3. Gets my bromine on there. Hit it with magnesium. We got our Grignard set. Good to go. All right. So how do we make an epoxide? All right. Let's do this. We got this. So hit it with a little bit of acid and gets our alkene. That's not an equal sign. It's ethylene. Hit that with MCPBA and boom, what's up? And boom goes the dynamite. And I think that's all, folks. So if you have any questions, please let me know. Yeah, these synthesis problems, the more you do them, the easier they will get. And if you get through all of them, try them again. Maybe just try a different route. Okay, and then of course, come to office hours if you want to run a synthesis problem by me. Much easier to go over in office hours than it is via email. All right, cool. Have fun. Bye.